So here we go with problem number 3. First of all, you need to balance the equation on this one. So if you look on the right side, there are 2 aluminums, and so you put a 2 here. That gives you 6 of these hydroxides, or 6, actually I'm going to leave that to last because you got H's here and you got H's there, so let's deal with the other things. I've got 3 sulfates. The SO4 groups stay together, so I could put a 3 here. Alright, so now we have to deal with the N's and the H's. So how many N's do I have? Looks like 2 N's. Right here there's 2. 1 times 2 is 2, then multiply that by 3 is 6. So put a 6 here. And then that brings us to our H's. The left side seems to be set, so we'd have 2 times 3 is 6. Over here you got 4 times 2 is 8 H's. 8 times 3 is 24. 24 plus these 6 is 30. 6 times 3 is 18, so here I would need 12 H's to make 30, so I put a 6 there, and that makes it work. All right, it says that we have 50 grams of the aluminum hydroxide, and we have 50 grams of the ammonium sulfate, and we're trying to find the volume of NH3, so that's question mark liters. All right, so you know, since you have quantities of both reactants, this is a limiting reactant problem. You have to figure out which one runs out first. So I'm going to change both of them to moles up above the equation here due to the amount of room I have. And when you're doing these, you're doing them on your own paper so you can spread out as you need to. All right, so I have 50 grams of aluminum hydroxide. Put grams here, put moles here, and 1 mole of that, if you add them up, 16 plus 1 is 17, 17 times 3 is 51, 51 times plus 27 is 78. Then the other one, we have 50 grams of ammonium sulfate. So you have grams of ammonium sulfate on the bottom, moles on top, 1. This one is 18 times 2 is 14 plus 4 is 18. 18 times 2 is 36. So 36. And then we had sulfur is 32. Oxygen is 16 times 4 is 64. So if you add those all together, you get 2, 8 and 4 is 12, carry 1, 4, 7, 7 and 6, 132 grams. Okay. So if I work that equals, so 50 divided by 132, over here our calculator, 50 divided by 132 is 0.379 moles. And that's the moles of the ammonium sulfate. Over here, 50 divided by 78, 0.64 moles of this one. So one of these runs out before the other. So you pick one of them. It doesn't make any difference really which one you pick, but choose either this number that's in pink right here, or here, the number in pink there. So you pick one or the other. I'll pick the aluminum hydroxide, all right, because it's first here. So get back on the screen, 0.64 moles of aluminum hydroxide. And what we're doing here is comparing one of these reactants to the other reactant to see, I'm going to see if I use all 50 grams of this, how much of this would I need? Well, we already know that 50 grams is 0.64, so really what I'm doing is taking the 0.64 moles here and trying to find out how much of that I would need to make the 0.64 go away. So I'd have 3, now 2, okay, so 0.64 times 3 divided by 2 is 0.96. Okay, so that 0.96 is the number of moles of NH4 ammonium sulfate needed to consume or use up the aluminum hydroxide. So now how much did you actually have of the ammonium sulfate? Well, I circled it over here. You actually have 0.379. So do you have as much as you need? No, 0.379 is not as much as that. So that tells you that as soon as this is gone, the reaction stops. The ammonium sulfate is limiting, and the aluminum hydroxide is extra. You've got more than you need. So let's go ahead and take our limiting reactant and do the rest of the problem. I'm going to try making this video just a little bit clearer, see if that makes it clearer, but it might not be as responsive. So here we go. All right, so take our limiting reactant, which we said was that one, 0.379 moles of ammonium sulfate. We're looking for the ammonia, so we're going to put mole. We're now in a mole ratio step. You realize first step was change to moles. So after we changed the moles and found what was limiting, now we're ready for the mole ratio. So moles of ammonium sulfate on the bottom, and moles of ammonia on top. That's a 6, and that is a 3. See the 6, see the 3. So 0.6379 times 6 over 3 is basically 0.379 times 2. 6 over 3 is 2. 0.758. So you have 0.758 moles of NH3. At this point, we're now where we were in a previous problem that I did, in that we could either use the 22.4 or we could use PV equals nRT. I'm going to use PV equals nRT because it takes less space. If you use the 22.4, that would give you the volume of gas at standard conditions. Then you would need to do the V1, V2, P1, P2 problem to change to lab conditions. All right. So we're going to use PV equals nRT. So PV equals nRT. So for pressure, in this case, we would use our 110. I'm going to leave units off because of lack of space here. So that's kilopascals. The volume we're trying to find. So put a V there. N 0.758 is what we just got right here. So that's the number of moles. Since the pressure is in kilopascals, you're going to use the value of R that is in kilopascals. So that's this 8.31. And then the temperature is 25 again, so it's just 298. All right, so how do you solve for V? You divide by the number that's with the V. So I'm going to multiply these three numbers and then divide by 110. So here we go. 0.758 times 8.31 times 298, and then divide by 110. 17.1 liters. So the volume is 17.1 liters, and that's your final answer for that problem. Again, you're looking at three steps. You have to change to moles, then do the mole ratio, then change to your desired unit. In this case, since there were two quantities, you had to change both to moles. And then when we had moles of gas, you could have used the 22.4 to find its volume at standard and then change it to lab conditions. Or you can just use PV equals nRT and solve for volume. All right, now the last question. You have to balance the equation again. So you've got 3 moles of that because there's a 3C, or you have to put a 3 here to get 3 carbons to match that. The oxygens, you've got 3 plus 3 times 2 is 9, and 3 times 3 is 9, so that's it. It's balanced. Okay, you want to make 40 milliliters of gas. That would be this carbon dioxide. And you want to know what mass of reactant is necessary, so you're looking for the number of grams of aluminum carbonate. What will you need to do first? You'll need to change to moles. So how do you change to moles? Well, first of all, this needs to be in liters. 0.04 liters. Or that's fine, 0.040. Technically it's 0.0400 because of the way I did the sig figs. All right, so 0.04 liters. Can you just go straight to moles by using the 22.4? Can you go straight to moles by using the 22.4? And the answer is no, because the temperature is not 0 degrees and the pressure is not 760. So what you have to do is either change this volume to standard and then use the 22.4. So like by doing that, it'd be like we did up here, where I showed you on this one. You can change it from lab conditions to standard conditions. The easier way, I think, is to use PV equals nRT to find the moles of gas. All right, so I'm going to do that right here. We know that PV equals nRT. All right, so the pressure is 750 torr. I just put a T there for torr. The volume is 0.040 liters. Remember now that in this PV equals nRT equation, volume always has to be in liters, temperature always has to be in Kelvin. We don't know N. The R value that we would use in this case, since it's torr, we'd go back up here and use that number, 62.4 liter torr per mole Kelvin. So that number is 62.4 LT MK, just for lack of space. And the temperature is 23, it'll be 296 Kelvin. You have to add 273. All right, now how do you solve for N? Would you divide by the numbers that are on the same side as the N, or would you divide by the numbers that are on the other side? Well, you need to cancel these, so you have to divide by the numbers that are on the same side as the N. So to do this problem then, watch my calculator. I'm going to do 750 times 0.04. So that's 30. And now I'm going to divide that 30 by 62.4, so divided by 62.4, and then divide again by 296. So my number of moles, N, equals 0.0016, and that's moles of CO2. Step 1 in stoichiometry, change to moles. We just did that. Okay, step 2 in stoichiometry is use the mole ratio. So now it's really, we're home free. We take our 0.0016 moles of CO2. We're going to put moles of CO2 on the bottom. We're going to put moles of what we're looking for on top. So that's moles of aluminum carbonate. All right, the number in front of the aluminum carbonate is 1. The number in front of the CO2 is 3. Then we need to change to grams of aluminum carbonate. So I'm going to put moles of aluminum carbonate here. And grams of aluminum carbonate on the top. Well, we've got to find the mass of the aluminum carbonate, so that'll take us a second. We have aluminum is 27, so we have 27 times 2. Carbon is 12, but there's 3 out here, so it'll be 12 times 3. Oxygen is 16, but there are 9 of them. So 27 times 2 is 54. 12 times 3 is 36. And 16 times 9 is the same as 160, be 144. So 16 times 10 is 160, so I just do 160 minus 16 gives me 144. So if I add those three numbers together, 10, 14, 6, 7, 8, 9, and 4 is 13, carry 1, 234. So there's 234 grams in 1 mole. Now we just do the math. So our final answer will be 0.0016. I just leave all these numbers in here because technically you shouldn't round until you're finished with all the calculations, but I've been breaking that rule, times 234, and then we're going to divide by 3. So 0.127 grams of aluminum carbonate. And that's our final answer for number 4. So I'm going to submit through Google Classroom another quiz. And that's the one that you will do if you need to redo this one or haven't done it at all.